Everyone, welcome to the last week of material for pre-calculus. We've got two kind of unrelated concepts to talk about today. We have limits at infinity, and then we have the intermediate value theorem. And limits at infinity kind of are just based on right here what we need to know. Vertical, horizontal, and oblique asymptotes. You've encountered vertical asymptotes. That's where you end up having those infinite discontinuities, where essentially the graph looks something like that and like that. And so like from the left it'd be approaching positive infinity, from the right it'd be approaching negative infinity. So you would just say either of those are unbounded. And today we're going to look at horizontal asymptotes and kind of oblique, but it's not necessarily a standard, but it is in a way estimating limits from values, and it's also in a way finding limits by substitution. So anyways, let's just see what's going on here. Before we do the assignment, we'll just talk about the basic rules, and the basic rules are actually the same rules that apply to horizontal asymptotes. If you're talking about an infinite limit, you're going to have some kind of probably rational expression. In other words, you're going to have some kind of fraction where you're going to have this like ax to the n plus blah 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 all the way down. Turns out it doesn't really matter what any of this other stuff is. It just matters what's going on right here. Actually, maybe I'll call it this. I'll call it t to use the notation I was using. And then let's say we have, I don't know, I guess I should use little lowercase b to the capital B. So just notice that the little b and capital B are different. Again, turns out all this stuff doesn't really matter. Could be anything, could be minus, could be plus, but really all we're saying here is the highest degree, all right, the highest degree term for each. So we're assuming these are written in order, like x to the 9th, x to the 8th, x to the 7th, so on and so forth, but the powers of x are descending. As long as you have the highest one first, the only thing that matters for infinite limits are what's going on with these exponents. So if the top exponent is greater than the bottom exponent, then essentially the limit, or we'll say the horizontal asymptote because it turns out the same thing, the limit at infinity or the horizontal asymptote is unbounded. Now that means it will either keep growing up forever or keep growing down forever, but essentially there's not really an HA, it's just moving up forever. There's no asymptote behavior, it's just going up or going down infinitely. Now if the top exponent is equal to the bottom exponent, then we have something really interesting happen. It turns out the HA is going to be y equals, it's a horizontal line, which means it's written as y equals something. The y equals a over b. So it actually equals whatever the numbers are in front here. And again, hopefully you remember that we've seen this before in Algebra 2 and actually in pre-cal, but it's actually the same rules for infinite limits, and there's one little detail we're skipping over, but we'll see that in a second. Okay, the last one is, what if the top exponent is less than the bottom exponent? Well, then your horizontal asymptote is y equals 0. Okay, now before we get to the assignment, again, I want to explain this maybe a little bit more in depth. What this really has to do with is something called growth rates. And what I mean by that is, the exponent, the highest exponent, is going to determine how things grow. Let's just do an extreme example here and talk about, what if I had something like 5x to the 10th plus 4x to the 5th all over, and then let's do 3x to the 8th. Well, no, I want to make it a little interesting. I think the unbounded ones are not interesting. So we'll make this 3x to the 11th plus 4x to the 5th. Now here's what I want you to think about. And I'll do it with a calculator in a second, think about what would happen if I plugged in, let's say, even a quote-unquote small number like 1,000. Think about this. I would be raising 1,000 to the 10th power. I would be multiplying 1,000 by itself 10 times, and then multiplying that by 5. So this number would be huge. Similarly, if I raise, 1,000 to the 5th power, that is still not a small number by any means, but it's actually comparatively so small that this won't even really matter if we're trying to go farther than 1,000. If we plug in 10,000 or 20,000. And in fact, maybe the best way to show you this is to actually show you just a graph of each term. So we have 5x to the 10th. We'll do it like this. We have 5x to the 10th. We have just 4x to the 5th. And then we also have 5x to the 10th plus 4x to the 5th. Okay, now, so don't get lost with me here. We're just seeing each individual term, and then we're seeing the terms. Oh, you know what? I need to do this in GeoGebra. GeoGebra has a better slide feature. I'm sorry. Let's see, GeoGebra Classic. Somehow, we're still going to actually get to this con assignment, and we're going to do it pretty quickly, too. Okay, so again, we have just the 5x to the 10th, then we have just the 4x to the 5th, and then we have the 5x to the 10th plus the 4x to the 5th. Now what I'm trying to show you is, it turns out these values are growing really, really, really quick. And we can see essentially, I don't even see the green. Where did the green go? Oh, actually, I think I see the point. If you look at this, the green and the blue are almost right on top of each other. In other words, they're almost the same value. We're going to zoom out and see that this isn't necessarily true. But you can, again, see that essentially the blue and the green aren't distinguishable from one another. Now, why is that? Here's the reason why. Again, what I was saying before, this 10th power is such a large number comparatively. When you add 4x to the 5th to it, it almost doesn't even matter. And we haven't even plugged in anything crazy like 1,000. We've just plugged in 6 and essentially seen that these two overlap. So really, I guess there's not a better way to explain this. This is what the 4x to the 5th is like contributing somehow by itself. You can see it looks way separate than this blue graph. But once you have this 5x to the 10th also contributing, its contribution is so much larger that you don't even really see a difference between just the 5x to the 10th and the 5x to the 10th plus the other term. So that's really all I'm trying to make out here. And what's the whole point of me saying all this? Let's dive into the Khan Academy. The highest power term is so much more powerful than the other powered term that it almost doesn't even matter when you want to ask what happens when I plug in big numbers. All right, so again, with that being said, the highest power term of each part of the fraction also is so powerful that it's not really going to matter. In other words, since this bottom power is larger, so I guess let's say it like this, if we're really considering infinity, we can now essentially say it's as if we're only looking at this. Okay, now with that being said, again, let's think about this. We're saying that exponents are the most powerful things here. And we're saying that a higher exponent is always going to outweigh a lower exponent really, really quickly. What that means is if you have a higher exponent on the bottom, that means you are going to have a much larger number. I guess I'll say, I usually kind of say very large. This is not a mathematical proof by any means, but it gets the point across. You're going to have a very large over essentially, I guess I'll just say small, because something to the 10th power is by no means very small yet, but comparatively it is. Now what happens when you have a very small number over a very large number? Well, let's just see what happens here. Again, I'm going to argue this by plugging in numbers that really aren't large yet, nowhere near infinity yet, but you can see I'm just substituting 10 into this equation. And so I'm getting actually a really, really big number. Okay, let's keep on going. So for a really, really big number there. Let's now plug in something like 1,000. Let's add a few more zeros. Oh, wait, never mind. Cut that out. I need to put extra parentheses around this denominator. I was a little surprised by what I saw there. Okay, let's try it again. Aha! Look at that. That is a very, very small number. Let's keep on going. Let's make the values inside bigger. Now, really all I'm doing right now, please hear me on this, is just explaining why all this is happening. Okay, when I add a 0, it gets one more 0 in the decimal in front of it. And maybe you would assume that that pattern would continue, and it would. If I add another 0, oops, another 0, now there's 4, you're going to expect another 0 in front. So the more zeros you add, the smaller this gets. So in other words, a small number, relatively small number, over a larger number is going to approach, so I'll say it's going to go towards 0. Okay, hopefully I've explained that enough-ish to get the idea. We've got 4 minutes because YouTube only lets me make a 15-minute video. Maybe I'll have to speed it up, but at the end of the day, all that matters is this chart right here. Now, sometimes I'll have to consider probably whether it's approaching from above or below. They do that sometimes. Whoops, we're not in calculus, although this is a calculus concept. Let's do limit at infinity of quotients. Armed with our table, we can do this pretty quick. Okay, as I approach infinity, positive infinity, that might matter later, what's going to happen? Well, again, we only have to worry about the highest degree terms. The top is smaller than the bottom in terms of exponents. So if the top is smaller than the bottom, the asymptote is 0. Okay, we have 7 examples to do. Well, let's get going. This time they're equal to each other, and so it's the 3 divided by the 1, the number in front divided by the number in front if they're the same value. Essentially because if these terms are the only ones that matter, again, think about it, if you rewrite it, if you say, okay, as I approach infinity, the only terms that will really matter over time, this problem is essentially this, if I only care about the highest degree terms. Well, look what happens. You can cancel out those terms. What are you left with? 3. So that's your horizontal asymptote as you approach positive infinity or negative infinity. Moving right along, this time the top is greater than the bottom. That's going to be unbounded. And we're just going to move through these really quick now. Top is less than the bottom, 0. Top is equal to the bottom, so divide the coefficients up front. Negative 6 over 1 is negative 6. Top is greater than the bottom, unbounded. And top is less than the bottom, 0. Okay, so it goes by pretty quick. I know I over-explained some concepts here. I really just wanted to understand, hopefully get you to understand the idea of growth rates. You know, again, if your top exponent is smaller than the bottom exponent, the bottom is going to grow so big, it's like putting a small number, even like a million, over a very large number, like a million, eventually. And see, what this means is 1 with 10 zeros before it with a decimal place. Essentially, write 1, but move the decimal place 11 places back. That's a very, very small number. So even if you have a big number, okay, even if you had $100,000, I don't know, and you're comparing it to someone else's this much money, Bezos money, then you essentially have no money comparatively. That's the idea, is you're comparing just how big they are to each other. Something with a larger denominator is going to essentially approach 0 over time as this gets bigger and bigger and bigger because the power just makes this grow so much faster. And then similarly, if the 11 was on top, now the numerator will be growing so much faster than the denominator. What that would mean is you would have a large number over a small number. And what that means is if you're trying to divide a large number into small pieces, you're actually going to get a larger amount of pieces. So again, think about this. If I have a very large candy bar that I'm trying to cut into very small pieces, I'm going to have a lot of small pieces. So that's essentially the idea. Hopefully it makes sense. At the end of the day, you can see that if you just follow this table, you can actually get through the assignment very, very quickly. But hopefully you understand a little bit of the why.